Okay, so this is a continuation from the previous video, and now we will explain the second part. That is, what is meant by this notation here. The second line, z is equal to x times y. What am I supposed to do? The answer is like this. We have this, as we said, this circle, and any two-dimensional plane. We make a circle on a certain plot. It contains x and y values, not everything, but it's certain values. Let's say the x goes from 3 to 7, the y goes from 10 to 19, and it could be not in all areas it goes the same, just a random figure that contains certain x and y values. That's our starting point for this whole discussion. And as we said, on that thing we take toothpicks. Each xy point, let's say 19, 7, x is 19, y is 7, a toothpick comes out from that point at a certain height. That's called fx of y. Okay, that's all good, but what are we supposed to do now with this x times y, and what is this z? The answer is we're doing here something much more complicated. We're going to take now in this plot, go around with a stylus, with a certain electronic device. Each point where the x times the y value is equal to 7, let's say, you can make a certain beep. If it's equal to 7 or less than 7, if it's equal to 7 or to 6 or to 5 or to 4. Now if you see this certain plot, since they're both in the positive, x is positive and y is positive, so definitely nothing will be negative, but you gotta be a genius to know which areas of this, which part will be equal to 7. I'm just gonna draw a certain random shaded area. Let's assume the area that I drew now, that area, if you multiply the x times the y, all these points, the value would be 7 or less than 7. 7, 6, 5, 4, whatever it is. That area. Anything outside that area, the x times y would be more than 7. Okay. Now, we wish to know what is the total volume of that area. So obviously we got to add together all the fxy's, all the toothpicks, all the heights of the toothpicks of this area. The heights times a tenth of an inch times a tenth of an inch, that will give us the volume of that shaded area. Once we get this concept, we can create a new thing here. Namely, we're going to say now, we're going to convert this two-dimensional into a one-dimensional. Why? Because x times y can be equal to certain numbers. Let's call that number z. And z can range from a certain point to another certain point. Let's say it cannot be less than 0, but let's say it can go from 2 till 96. I don't know. Maybe this edge here, this top edge where it's darkly colored, that's the area where it's x times y is equal to 96, 97. let's say the uppermost point, x times y is equal to 98.5. That's the highest value x times y can go. That means we got here a new line take a look at the bottom. There is a z line. It goes from 3 to 98.5. And this z turns to be a new distribution. Why? Because this will contain all the probabilities of z. That means of x times y. So if somebody will ask us, tell me what is the volume of take a look at the bottom, and this is the z, and let's say somebody will ask us what is the volume of the numbers that are x times y is less than 17, from 17 to 3. So as you see, it is the ones that goes from here to here, this whole area. That is the volume of 3 to 17. And actually, since there is the area from 3 to 17, we can also talk about 17 itself, the height of the line that says 17. What is the height of this 17 line? I'll make a mark on it. I made these two lines to show you what is the height of that line. So that's going to be the fz, the small fz. That is the height of each number z. From example, here we're discussing 17. What would be the f of the z? That is the small f of the z, but that means the height of z at a certain point. So what is the moral of this story? That we converted this whole situation into a new function, and we took actually a two-dimensional thing, made it into one-dimensional. Because now we're only discussing about numbers from 3 to 98, and we don't care anymore how the number 17 got generated, through which x and y. It can be many x and y's, different combinations that spell out the number 17. What we're interested in is we want to take this 17 and add them all together and bring them down right now downstairs and in the z graph, and tell us what is the total of the area that is equal to 17. That is a different way of looking at it. Before I said 17 and less, but here you can look at it a little bit different. I'll explain myself better. You see, I made here a wavy line. It says 23. What does that mean? It means every single point on that wavy line, the x times the y will be 23. So I have here a certain wavy line that the x times the y is 23, but all of these are actually toothpicks. So So we can talk about adding together all the toothpicks. But here we will not multiply them by a tenth times a tenth. You just want to stick to the surface area of all these toothpicks together. That will be as you see, I wrote 23 in the bottom. That will be the height of that 23 line that is wavy. The same exact of all the toothpicks added together, not imagine you put the toothpicks on a table and you look at the surface area that these toothpicks take up from the table. That exact surface area, that is a certain number, right? It can be 39, 45, the surface area. That will be exactly the height of this line of 23. So you can look at it like I transformed that surface of the wavy area into a simple point, a simple toothpick that is passing, that is standing up when Z is 23. That is what happens with this business. I just said the same thing in different versions. Somebody who understands how calculus works will see that it is one and the same thing. It's just said differently. You can look at it whichever way is easy to understand. Either you can look at it like I think it's easier to grasp in the mind in the way of saying anything less than 23, the volume of less than 23 will be here also anything from 23 in the bottom, from 23 to 3. That area will have the same percent. Let's see, it will be 48%. The same will be if you measure from 23 till the end. The volume will also be 48% of the whole mountain. That's another way of looking at it. Now, here comes the amazing fact. So really, if somebody would ask you right now, what is the expected value of this new distribution of Z, it might be quite troublesome, because it's murder to find the distribution of Z. I just made a nice wavy line, but it doesn't know what it is. Sometimes even from the easiest ways, from the easiest x and y's, it's hard. Let alone if it's complicated, it's very hard to get to know the actual f of Z. Then you must multiply the f of Z by Z and going through from 98.5 till 3 to get the expected value. As the rule tells us, to find the expected value, you must go through all the values and the f of that thing. Let's say here it's the f of Z, but that's extremely hard to get, the f of Z. You multiply it times Z, and then you integrate it from 98.5 to 3. That is even if it's possible, it's hard, and I guess most of the time it's impossible. So here comes the amazing trick that tells us, forget about it. You don't need to go through that difficult task. Just use the fxy times xy. Just do it without knowing even fz. Just take fxy, as we said in the first video, that we know because it's given. Make times x times y, and go through integrated the whole area of x and y. Hopefully that won't be so hard. And you'll get exactly the same answer, because in essence you're doing the same thing. It's just a matter of how you're doing it. It's either you're going through this windy road, you're trying to nitpick in this circle to find out all the points where x times y is 23, and then you take that whole thing and you multiply it by 23, that's the z times the fz. Or we say, just why do you need to go so windy? Let's deal with each single toothpick as an individual toothpick, and that will be fxy times x times y. You get the same answer. Think of it. Think of it like here you're dealing with each single toothpick separately, and here you're dealing with a collection of toothpicks. All the toothpicks that the x times the y gives us a certain number, let's say 23, and we're saying why should we go through each toothpick, make x times y times fxy. Let's take all the toothpicks together that are all these randomly scattered toothpicks that are equal to 23, and let's multiply them by the collection of the fz, that is the surface area of all these toothpicks together. It's doing the same thing. It's just doing it to like trying to do trying to grab in a lot of things at once. That just gets you complicated. But that's what you're doing. You're just trying to. Sometimes a person wants to do things very fast, and it gets much slows down the process. So you want to grab together a big slab of toothpicks that are all that their x times the y will be equal to 23. Multiply them by the surface area. That would be like, in essence, like slicing each toothpick into small thin and finding the fxy. And then you do this to all values of z. It can go from 3 to 98. It's just doing the same thing in a different sequence or in a different method. So the exy is the thing that can be done very cleverly without getting to know the distribution of z. Other stuff, however, impossible. Somebody will ask you, what's the probability that x times y is less than 15 or 14? You gotta do it the long way. You can use the expected value as an approximation sometimes, but you cannot get the real answer without figuring out the z function. That is this going through a very windy process, extremely windy, to get exactly to know what is exactly the f of the z. First you find out the capital F of the z, and then you can figure out the derivative. You find out the lowercase f of the z, and that's how you can get to know this distribution. Thank you very much for listening. Enjoy yourself.